So we're back talking about alcohols. Who would have ever thought you would have had a conversation about alcohols for weeks on end in a chemistry class? But not the alcohol that you're thinking about, I hope. I hope none of you were alcoholics. Alcohol is kind of bad, right? I mean, you might think that this is great and fun and everything when you're young, but sooner or later it's going to catch up with you. So, prove organic that there's other things in life other than alcohols, but it seems like right now the only thing that's really taking up our time is alcohol after alcohol after alcohol, and we might become alcoholics just in organic lecture theory. That's just the way it seems, and that's the way it is, especially at the beginning of the semester in a huge chapter that devotes itself to alcohols left and right. Now, the issue here is that the alcohol that you drink, if you do drink it, is something that looks like this: CH3CH2OH. All right, well, what type of alcohol is that? Primary, secondary, tertiary? What is it? Well, you're going to look at this OH and you're going to say, oh, that OH is on a carbon and that carbon's attached to only one other. So this is a primary alcohol. Yes, that's right. And if I had to name this, this is a 2-carbon chain. So this normally would be called ethane, but I drop the E and I add OL, and that's called ethanol. And ethanol is drinking alcohol. That's what's sold at the ABC store, or made up in the mountains of West Virginia, and North Carolina for that matter too. So here we have our first example of a primary alcohol like ethanol, and we're going to undergo an oxidation reaction with it. Okay, so they're going to draw an arrow and they're going to go, well, we're going to react this with H2CrO4. Chrome, there you go. What does chrome do? It increases the number of C to O bonds. All right, so what this structure looks like is a CH3, a CH2, and there's an OH on that last carbon, right? This is just a different way to draw it, just to make it match the template that we've been doing. That's the only reason that I did this. So in the other examples, we said, there's the OH, bing, there goes the hydrogen, away it goes, bye-bye. And then here we have a carbon that has 2 hydrogens, and we need to get rid of one of those. So, bing, there you go, it's got one left. And we increase the number of C to O bonds by drawing an extra line. A double bond forms. That carbon becomes like an sp2 carbon now. Well, this is not a ketone. This is a carbon double bond O with a hydrogen on one side. If a hydrogen is on one side of it, folks, this is called an aldehyde. So this makes an aldehyde. So that ethanol structure will oxidize in the presence of chromic acid, and that oxidation product is going to be an aldehyde. No, there's no difference, right? You're looking at this and you're going to go, wait a minute. I did this the same way as I did all of the secondaries. Yeah, you did. You did. That's good. But, like I've said before, there is a hydrogen that's still on that carbon. And we still could remove that disposable, nasty hydrogen that nobody wants and increase the number of C to O bonds yet again. And the reason is because when this product is formed, this product is still in a flask or container or reaction vessel with chromic acid. That chromic acid's not going away. This chromic acid, you have quite a bit of it. I mean, think of it almost like a solvent. You have quite a bit of that. And when this molecule oxidizes, we make a product, and that product is exposed to that acid yet again. So we can further the oxidation in round number 2. And that's how I'm going to write this. Round number 2 with H2CrO4, just like before. So our product here is our CH3CH with a double bond O. And the way that we increase the number of C to O bonds is that we erase that hydrogen, bing, there it goes. And we increase it by adding an OH group. Another way to look at this, there's a hydrogen that was right there, wasn't there? Here was our hydrogen. And in second round of oxidation, you increase the number of C to O's. Well, that C to H bond right there, and oxygen is going to squeeze in the middle. And there it is. There is your round 2 product for the oxidation of a primary alcohol. And this makes a carboxylic acid. That is the C double bond O with an OH. So, quick recap. Primary alcohol oxidizes in the presence of H2CrO4 chromic acid to make an aldehyde, and then that undergoes another oxidation reaction in order to make a carboxylic acid. Now, as I've said before, I've hinted, maybe, just maybe, we don't want that to happen. If we do not want that second oxidation step to happen, we can put a stop to it. We don't have to let it get out of hand. We can show it who's boss, and that boss is you. And the way that we do that is we include a reagent, and that reagent is going to put a stop to all of the madness that begins to happen here. And that reagent has an abbreviation of PCC. And P stands for pyridinium or pyridinium. C stands for chloro. And the other C stands for chromate. I see the chromium again. Chrome. I see that, right? Pyridinium chlorochromate. So even if they do not write sulfur or the sulfuric acid, sodium, potassium salts, even if they do not write chromic acid onto the arrow, and let's just say they put PCC there. Well, PCC is the chromium source, and they are making an assumption that you know this is somewhat of a chrome-based reaction, just like all the others. But this reagent is kind of special because this does not allow the second oxidation to take place. Now, PCC, this has to be included in a solvent, and sometimes they will write the solvent as DCM, which stood for dichloromethane. Very common solvent that we use in the lab all the time. And DCM has another name that it can go by, and this name is called methylene chloride. Now, they do have an abbreviation for methylene chloride, and it's MECl2. So it is paired, and it is paired with a solvent. They do write that solvent on the arrow a lot of the time, and that PCC will always be, or it should at least always be, with a DCM or a MECl2 abbreviation. And that is what that stands for. So nothing happens after that first oxidation step. You get the same product. You get the same product in the first step. There's no difference in it. You target the hydrogen, you erase it. You target the other hydrogen, you erase it. You draw that double bond. This happens the same way. There is no difference. The issue is that this prevents the second oxidation from happening. So you do not get the carboxylic acid product that you would normally get if you just let this run rampant. PCC is there to stop it. Now, if you've noticed, what I did is I started with ethanol, the drinking alcohol, and I did that for a reason. Not really kind of told you why yet, but that's to come. But I just want you to keep that in mind. We started with this reaction. I started with that description for a purpose. And that purpose we will circle back around to at the end of this video. Now, you know me. There was the reaction. Now we question why. How? How does that go forward the way it goes forward? Well, we're going to start with chromic acid. All right, so chromic acid is Cr in the center. And chromium is one of those that really doesn't behave in the octet. It's something different. So we'll put an OH there, and we'll put an OH here. So this is H2CrO4. This is chromic acid that we are using for the oxidation step. Now, you need to keep in mind as well, there's another chromic acid that's out there. So here I'm going to put H, and then I'm just going to put a blob for the rest of the chromic acid that might be present. The funny thing that happens here is that we somewhat have a base and we somewhat have an acid, and we see this kind of game of toss back and forth using that hydrogen that's acidic. Okay, so what I mean by that is that this oxygen has some free pairs. We've seen this before. And that oxygen says, I'm not happy, I need more. More, Daddy. Did you ever see Willy Wonka? Yeah, okay, you get my drift. So this oxygen has some free pairs, and those free pairs are negative, and that negative area wants something positive, and this other chromic acid says, I've got something, look at me, I'm an acid, I can donate this proton. And oxygen says, okay, hydrogen, how about we make a bond? Okay, and there it goes. And these electrons will shove in, and it will go on away with the base, whatever you want to call that. Well, when that step happens, when this step happens, the chromic acid structure changes slightly. So once again, we're trying to explain how this actually happens. So I've got this oxygen that now has this extra hydrogen, and now oxygen realizes, oh no, I made a mistake. I've got 3 bonds and I don't need 3. I need to break something off. And that oxygen looks at the relationships that it's in. There's 3 of them, a chromium and 2 hydrogens. And it says, I'm electronegative. I want. Which one can I push around the most? And it looks at chromium and it looks at hydrogen and it says, hydrogen, you don't put up too much of a fight. So I'm keeping you around because I can have my way and you're not going to say anything about it. So that OH with the hydrogen, just like all the other times, is now a water molecule that wants to leave. Okay, well that's great, because at this point, what I have here is also an alcohol. So CH3, CH2OH, and that oxygen, just like before, has some free dots. So this oxygen, electronegative, electron pairs, carries a partial negative, looks at that chromium molecule, and it goes, oh, it's vulnerable. It's in trouble. Now's my time to act if I really want to get in on this. So this oxygen says, hey, chromium, hey, you're spread too thin. That oxygen up on top wants and wants. The oxygen to the left wants and wants. The oxygen down below want and want. And now you've got this other oxygen that wants and wants. And that oxygen actually was so unhappy that it went out and found somebody else too. What are you doing? You just need to tell that OH group to go away because it's found something else. And you just need to let me come in and kind of satisfy that need for you. And that chromium goes, okay, that sounds like a good idea. So we have, at this point, really an SN2 reaction that happens. A back door. Chromium is in a relationship. That relationship that's on the rocks is with this protonated alcohol group at this point. That protonated alcohol group is on its way out, as we see the alcohol group come through the back door. It all happens at once. Walden inversion takes place, if that's what you want to talk about, but it is an SN2 reaction. So this is the whole concept of my alcohol now interacting with the chromic acid. And what I end up with as a product, okay, is this chromium that has a double bond O. The OH is still there. Nothing's changed. Except now, this alcohol group, OH, CH2, CH3, has been substituted for that protonated alcohol that was there already. And that really wasn't an alcohol group, right? Just to be clear, it wasn't really an alcohol group, but it was an OH. Well, as you can expect, here in this step, that oxygen says, oh gosh, I made a boo-boo. Look at me. I made the same mistake all over again. I never learn. So that oxygen has 3 bonds. It doesn't like the 3 bonds. It looks at this concept and it says, okay, what can I get rid of? Hydrogen, you're disposable. So let me just get rid of you. This other carbon and this chromium, you know, it might meet my needs a little bit better at this point. I need to get rid of something that's fairly easy to get rid of. And I'm sorry, but you got to go. Well, what takes that hydrogen? You remember this little blobby thing up here that donated the proton in the beginning? Well, that little blobby thing is going to come back. And it's going to go, hey, I'm carrying a negative. Don't forget about me. You know, I gave you a proton in the beginning, and that's what started this mess. And I think I would like the proton back. So here in this part of the mechanism, that goes up to the hydrogen, pulls the hydrogen off, oxygen in this hydrogen bond gets destroyed, and those electrons get shoved up to that oxygen to make the oxygen happy. Okay, so we're getting closer. We're getting closer. So here's the OH group, my chromium, double bond O, oxygen, CH2, and CH3. Still has a free pair here and still has a free pair there. Now what happens? We're getting closer. Keep in mind, the whole object here is to explain how a double bond gets formed. Can you, just think about this for a minute. In the previous examples, what did we do? We looked at the OH, we looked at the carbon, and I said, erase this hydrogen, bink, erase this hydrogen, bink, and draw a line. That was easy. Okay, well, we took things for granted. This is what we took for granted. How can we bink, bink those hydrogens off of there and draw a double bond? You're just going to take my word for it? No, we've got to kind of explain why this happens and how it happens. That's, again, the purpose of the mechanism. That's why they're so important. Okay, so I see this newly formed kind of intermediate in a way. This alcohol group that's not really an alcohol anymore. It's lost the hydrogen. Part of this chromic acid has now been destroyed. It's not really chromic acid anymore. These two things have joined forces. And if you remember, one of the things that I told you here is that for this to happen, you have to remove a hydrogen from an OH group, and you have to remove a hydrogen from the carbon that's on it. We've not really done any of that yet, but we're getting ready to. So in this part of the mechanism, see the CH2 that's right there beside of that oxygen? I'm going to erase that, and I'm going to draw that hydrogen pointed down, still 2 of them, but I'm going to put a focus on the hydrogen in that carbon. And the reason is because there's still a blobby thing out there. And that blobby thing came just like before, probably from chromic acid that served as an acid and donated a proton. And that's going to come around and say, well, shoot, A blobby thing beat me to this already. That blobby thing already took the hydrogen off of that oxygen, and I came around, but I'm too late. And this molecule is going to go, no, we actually do have an extra hydrogen that you can take. We have an acidic hydrogen, and the reason that we have an acidic hydrogen here is due to electron withdrawal. Do you remember that from Chemistry 251? What that meant is that here is an electronegative atom, here is an electronegative atom, here is an electronegative atom, here is an electronegative atom. And all of those electronegative atoms are going to suck all the way through the molecule, and all of those electrons go to that side. And this carbon feels very vulnerable because these electrons are getting taken away from it little bit by all of those greedy ones that are all the way over there to the left. And because it's sucking those electrons through, that makes this hydrogen an acidic hydrogen. That is why it can donate that acidic hydrogen. It's due to all of those greedy electrons that are in that molecule. Okay, so this blobby thing comes in and says, another blobby beat me to the first step. Please, can I have some more? And that molecule goes, yes. Take this acidic hydrogen and be happy. Now go away. So that blobby thing goes, takes the hydrogen. That hydrogen is ripped off from the molecule. This pair of electrons has to go somewhere. That set of electrons go in between the carbon and the oxygen to form a double bond. Ding, ding. There's your oxidation step. And this oxygen says, I'm getting ready to create an extra bond. I cannot have 3. I should only have 2. I've got to get rid of something. So chromium, you have all of those greedy oxygens on you. You're going to have to take those electrons and you're going to have to go. And it leaves. All of that happens at one step. Folks, this is how the oxidation is formed. And what we end up with at this step is my CH that now has that double bond right there, and then a CH3 on the other side. So this is a very long, drawn-out story, isn't it? A simple little reaction, bing, bing, draw a line, ends up being a multi-step mechanism with a lot of moving parts. The other thing that I also want for you to take home and remember, kind of appreciate it at least, is that when we started off with this reaction, CH3, CH2, OH, we put chromium on it, and we ended up with CH3, CH2, double bond O, but it's not really a CH2 because I had to erase one of those. That's the product that we ended up with. You need to understand that this oxygen is not the same as that oxygen. They're different oxygens. How do I know that? Look at the mechanism. In the very first step of the mechanism, this oxygen comes around, that associates with the chromium. That chromium has oxygen as well that it's getting ready to leave and donate. And then we end up with this product, and this product is now a double bond O. Does that make sense? No, it does not. Are you paying attention to me? No, you probably aren't. I could tell you anything that I wanted to tell you and you would believe it straight up the bat. No, they are the same oxygens, folks. That's the story. So it is the same oxygen because look at this. I'm going to circle them. Here is the oxygen that's right there. Again, are you paying attention with the mechanism? Are you following through and being an active listener? This oxygen is going to go on to the chromium. This is that oxygen because there's the alcohol group. That oxygen is the hydrogen that gets removed. Those electrons get shoved up, and that is what creates a double bond, right? So here is the oxygen that is carried through all the way with the mechanism. It's this oxygen on the chromium that does not stay. That leaves in form of water for this mechanism to go forward. So they are the same oxygens. They should be the same oxygens. The only thing we're doing is increasing the C to O bonds. But folks, it's questions like that that the mechanism can tell you the answers to. And if you don't fully understand mechanisms, you will not know the answers to those types of questions. And again, those are very, very important. Now, in this whole mechanism reaction of oxidation, we also talked about this PCC. And here's the structure of pyridinium chlorochromate that we call PCC. So pyridine, and pyridine should not be an uncommon acquaintance to you at this point. It's the same thing as what we've always used, except this is a pyridinium, not a pyridine, which means it's an ion, and that's why we see a NH with a positive charge. And then we also see the chlorochromate piece, which is CrO3Cl-. So we see a positive and we see a minus. That makes it an ionic compound, and that ionic compound can dissolve in solution. We call this a salt, and this is another reason that we need a solvent in order to make this dissolve in solution. Now, we can't use water as a solvent because we're talking about organic chemistry, folks, and water and organics typically do not mix. So that is why the solvents here are methylene chloride, also known as dichloromethane. These are organic. That is an organic compound, and that organic compound is the solvent. So these organic reagents can all have a swimming pool to basically react in. So that is the structure of pyridinium chlorochromate that we call PCC. So again, we use that with primary alcohols. So in that previous example, we used ethanol. That is not where ethanol would stop. Ethanol would oxidize again under the same mechanism somewhat, and we would get a carboxylic acid that would form. But if we threw in PCC, and remember, this is DCM or MECl2, it means the same thing, different names. That can also be represented as CH2Cl2. It's all the same. Do they give you the structure? Do they give you the abbreviations? What do they give you? But PCC stops it, and it ensures that this oxidation only happens once, and you get a C double bond OH, which is the aldehyde. All right, so that's the purpose of PCC when it happens. So let me go back. Here we have CH3, CH2, OH, and let's say that we add chromic acid. So that would give me CH3, CH, double bond O. But it doesn't stop because that was a primary. It would happen again if I'm not careful, and that product would end up being CH3 carbon double bond O, and instead of that hydrogen, that would be an OH group. Okay, so now let's go full circle. This is ethanol. And that ethanol, CH2CH2OH, could oxidize, and that could oxidize into an aldehyde, and that aldehyde could then oxidize again into this that's called a carboxylic acid. This is CH3COOH. Do you know what the name of this structure is? CH3COOH. Folks, this is acetic acid. Vinegar. just strong vinegar. So if you've ever been around somebody drunk with a hangover, maybe the next day, and you smell the drunk smell, maybe coming from the breath, not very pleasant. You don't want to wake up to that either. But if you've been with someone that drank quite a bit the day before, passed out, woke up the next morning, and you smell them, whether it's coming from their breath or whether it's coming from the pores of their skin and oozing out, and if you've been around those people, you know exactly what I'm talking about. That smell, folks, is partly due to that acetic acid. Their body has oxidized the ethanol that it has consumed. And all of this dizziness and all of this kind of getting sick at my stomach, nausea, headaches, all of that mess, all of that is due to the prevention and the buildup, the prevention of the acetic acid and the buildup of the middle step. And that middle step is an aldehyde. And that aldehyde can be very poisonous to a human body. And that's why some people have to go to the hospital because they're drunk sick. This is why. So now we're kind of relating real life stuff to actually what goes on in a human body because we are walking organic chemistry labs on the inside of us. And here's just one of many of those examples. So drinking alcohol gets oxidized to an aldehyde. That aldehyde buildup, the faster that builds up, the more symptoms of drunkenness that you get. And then your body will take that molecule, oxidize it again to give you a carboxylic acid that is called acetic acid, which is vinegar, which makes you stink. Oh, the wonders of drinking. Doesn't that sound attractive? Okay. Well, what I want to do in the next video is go over some examples. And I want you to take a stab at them. Here they are. It says, give the product formed from the reaction of each of the following with acidic solutions of sodium dichromate. 3-pentanol, 1-pentanol with and without PCC, 2-methyl-2-pentanol, 2,4-hexane-diol, cyclohexanol, and 1,4-butane-diol. So this problem is going to test you on a number of different things. Number one, you were supposed to learn how to name alcohols in Chemistry 251. So this question is going to come around, and it's basically going to say, listen, you remember that stuff back in the day? It's coming back. So can you take the name and can you draw an alcohol from the name? Don't Google these. Don't wiki them. Try to do them yourself. Can you draw the structure of 3-pentanol? If so, you're one step closer to predicting the product. And then take that alcohol, react it with sodium chromate and acid, and tell me what product is formed. So there's your homework. Try those questions. See what you come up with. Test yourself. And then in the next video, plus pray, double check your answers. And I know that you're going to give me correct answers for every single one of these. Now go away and try them. And then come back. Don't go away forever, please.